So, good afternoon, everyone. Myself Sana Sheikh, and I'm a second year PhD student from IIT Bombay, and I'm doing a NPTEL course live session for a course named Mechanism in Organic Chemistry, and the course instructor is Professor Nandita Madhavan from IIT Bombay. So, this is our 7th week live session. On every Saturday, we are taking live session from 3 to 5 p.m. So, in today's live session, we are going to discuss the trapping effect. This heavy item effect we have done in previous class. Now this is a trapping effect. So as we have discussed, trapping is used for finding the reaction mechanism, right? So which type of trapping will be required? So here you can see we are trapping for trapping an intermediate. We have discussed for radical, cationic and anionic, right? So here we are going to discuss the trapping for the intermediate other than cationic, anionic and radical intermediate. So if intermediate is not cationic, not a anionic form and not a radical, then how we can trap the intermediate? So this is the first example where we are going to trap the benzene. If you know the structure of benzene, you know it has 4 pi bonds in its structure. That means it is not here you can see there is no cation, no anion or no radical formation is there, only the intermediate. So for this type of intermediate we have taken one reaction where here diazotization is taking place, and here you can see elimination by elimination of the these group we are getting a dinophile which is benzene intermediate. Why we are call it dinophile? Because it's normal benzene but one pi bond is here which is behaving as a dinophile. Dinophile always have one pi bond, one pi bond participate in a reaction. Okay, so here dinophile formation along with CO2 elimination and N2 elimination. These are gases. So when this dinophile will react with diene, it will give a adduct and it will undergo 4 plus 2 cycloaddition reaction, which is also known as Diels-Alder reaction. So how we can find out the in benzene intermediate? By reacting it with the different diene to get the particular product. So we can predict that the our intermediate was the uh, benzene benzene intermediate. So this is a type of trapping here. Now let's talk about the trapping in biology, application in biology of trapping. So now here we have nucleic acid hydrolysis. So you can see here this OH will attack on phosphorus, and this oxygen phosphorus bond will break and O negative will generate over oxygen. Then after getting this O negative, this minus charge will again push electron over here, and the this whole group will get eliminated, right? And we will get some intermediate. In after getting this elimination, we will get intermediate. So how we can prove this intermediate formation? So here uh, we can use the phosphorin trapping. What happened in phosphorin trapping? Like suppose we have here our our starting material, and then when OH is attacking on phosphorus, this O minus is generated over here, right? Then this O minus is nothing here, our intermediate, right? When O negative will generate over here, it will give a intermediate. Then if we will add some trapping agent like chloroacetate, we will observe that it will attack on carbonyl carbon, followed by the elimination of chloride ion to give the corresponding P1 intermediate. So we can say we have this as an intermediate if we are getting P1 as a product. So this is nothing but the trapping of intermediate. Here in similar case, if this is not the intermediate, suppose if we have this one as a intermediate, then if we will react this intermediate with the acid chloride, sorry, chloroacetate, we will observe that here O minus OH will trap the acetate ion followed by the elimination of chlorine to give the P2 as a product. So by adding a different trapping agent, we can find out the mechanism, or we can predict the intermediate structure, and we can find out the exact mechanism followed by the reaction. Now here, clever reactant design to trap intermediate. So reaction have designed in such a way that we can trap the intermediate. So here we have mandolate racemase. So S mandolate conversion to R mandolate. So first of all, you should know what is mandolate. So here mandolate structure is there given here. Model reaction. It is a model reaction, and we have this is a S mandolate. Backside you can see this bond is at backside, right? Now we have to convert in a R mandolate. So first of all, what will happen? Racemization. So racemization will give an intermediate which will have a carbon ion. So here you can see if proton abstraction will takes place from here, negative charge will generated over here, right? At this carbon, I will draw here, right? When negative charge will generated over here, it can undergo resonance, right? It can undergo delocalization to give the resonance structure, and this bromine will knock out. Correct? So this will be our intermediate. Then after getting this intermediate, then you can make a attack of bromine. Here again it will go this way, and again that proton will be, this negative charge will be protonated by H. So with reaction with HBr, this reaction with HBr will give you a racemic mixture of mandolate. So here that this reaction is called a mandolate racemase. So that's why here how you can predict the product by finding out the intermediate. So this is a clever trapping design called mandolate racemization to find out the reaction mechanism. Then we have example here, competition experiment. What is competition experiment? When we are doing some reaction and there are possibility of formation of two different products with same speed or same stability. That is called a competition experiment. So whenever we are discussing about the tertiary carbocation reaction, we observe that we have learned SN1 and even reaction, even type of reaction. So SN1 means substitution, nucleophilic substitution reaction, and even means elimination reaction. So both the reaction happen only when the stable carbocation generation is taking place during the reaction. So here we have tertiary substituted group here. Tertiary substituted carbon atom which have leaving group. When leaving group will eliminated, we will observe the formation of intermediate, that is carbocation, stable carbocation. Then this stable carbocation will either be get trapped by leaving another leaving group to give the this we cannot say leaving group, nucleophile, yeah, nucleophile. It will get trapped by the nucleophile to give the SN1 product, or otherwise it can undergo elimination of this proton. Suppose here we have two, here proton, elimination of elimination reaction to give the even product. So here we have a competition between both the products. So if you will see here, in these cases, when leaving group are chlorine and bromine, we are getting both the product in almost equal ratio. But when we have a different leaving group, that is a dimethyl sulfur, here we observe the different yield. That means the substituted product is a major product. Why is this the case? So here we have, when we have the chlorine and bromine as a leaving group, so they are contact ion pair. So they are very close to the carbocation and they make a intimate ion pair. When this is the case, so here it can it can abstract the proton, because it is a carbon ion managed charge species, so it can take the proton to get stabilized and it will give the eliminated product as well, that is even product. So that's why here even product ratio is very high compared to the third case. When talking about the third case here, because it's a very large group, it is not in a contact ion pair, and because of the distance with the carbocation, it cannot take the proton and it's not giving a even product as much as high compared to the chloro and bromo case. So that's why in case of SME2 we are observing the mostly substituted product as a major product. So I hope you are clear here. So here in this case what we have discussed, with a common intermediate we get two different products, right? Now we are going to discuss the common product with two different reactant, common intermediate with two different reactants. So if two reactants give the same product, it indicates that both the reactions go through the same intermediate. So we will discuss some example here. The first example is solvolysis reaction. In this case, you can see formation of carbocation is taking place, right? N2 elimination will takes place here and it will give here positive charge, right? Positive charge. So this is a carbocation. Now all of you know that this is a primary carbocation. So there is a possibility for the migration of adjacent carbon atom to give the stable carbocation, right? So all of you know that primary carbocation is a least stable carbocation compared to the secondary one and tertiary carbocation. So secondary carbocation is more stable, so it can migrate to this carbon atom to give the secondary carbocation. So this is also the possibility for the intermediate. Then the third possibility is that this like its type of hyperconjugation we have discussed. So here this bond breaking will take place and double bond will generated over here and positive charge will generate over here, like this third case. So this is also the possibility, but not that much high, because here primary to primary carbocation formation is taking place. So this is not that much stable, that's why we are observing only 4%. Now after generation of this carbocation, this carbocation will be trapped by a water molecule. So yeah, at the end, all of you know the mechanism, I hope, because we have discussed many times. So try to solve the mechanism by yourself. It will be for your practice purpose. Now after trapping of carbocation by H2O, we will get different products, that is 48% of this product, 48% of this one and 4% of this product. Now is these are intermediate and products formed by this particular reactant, right? Now we are going to take a different reactant here. This is a 4-member cyclic ring attached to diazo N2 diazo compound, right? Now we have 4-member cyclic ring. So here also the strain was there, here is also strain is there. Now suppose if we have this intermediate, what will happen? N2 elimination will takes place and plus charge will generate over here, correct? This is the first intermediate we can observe from this reactant. The other thing is possible here, After getting this carbocation, this bond breaking will takes place, right? And double bond will generate over here, this position, right? And it will give this as a intermediate. The other third possibility is also there when we are taking the different reactant. Like here, if we have this butene, OTS substituted butene. So here what we will observe, this OTS elimination will takes place and give the formation of carbocation over here, right? Is this same with this one, right? This is the same intermediate. Now again this carbocation can be undergo isomerization to give the this cyclic propane intermediate. It is also possible here, and carbocation will generate over here, right? So all these three carbocation formation can take place during these three type of reaction. So that's why here we can say the intermediates are common, and product will also be a common for this reaction, but the reactant are different. So this is a solvolysis reaction example where the formation of carbocation taking place, which is a common intermediate for all three substrates, all three reactants. Okay. Then we have discussed the second example where the rhodium catalyzed allylic alkylation reaction is taking place. So here, sorry. So here you can see we have pi-allyl system, right? Pi-allyl system. Why we call this pi-allyl system? Because with oxygen you can see this is a allylic bond and pi bond is there, so pi allyl system it is called. And here we have a catalyst, that is rhodium PPS3 chloride. So what will be the intermediate in this case? So one possibility is that this pi bond will be distributed in all three carbon atom like this way. So this is the pi allyl M complex, right? Metal will bind through this double bond uh, which is in resonance with these three carbon atom, which is delocalized here, right? The other possibility is that pi plus sigma plus pi complex, right? So here in this case, uh, this metal will be made form bond with the carbon atom with sigma bond, plus pi bond will also be form bond with the metal with coordination bond. So this is a sigma plus pi complex. The other possibility is that in this carbon atom it will form metal bond, and then pi bond will be uh, will shifted towards this carbon atom, right? This way, like this. Here it will shift this way. Okay. So these are three possibilities. So these two are almost equal. So here we will discuss which is the correct intermediate for this reaction. So if pi allyl formation, pi allyl M complex formation will takes place. So if we have the other isomer of this intermediate, sorry, this substrate. So this is the other isomer, right? You can see here. So here we have isopropyl group on other side, where in this case we have isopropyl group on this side, right? So this is the different reactant. So if the pi allyl formation, pi allyl M complex formation will takes place, so here we should get the same product. But when the reaction was done with this reactant, we have observed that the different product formation, which is this one in 97% yield. While performing this reaction with this first reactant, we are observing this is the yield of intermediate product, with 97% yield, right? So if the pi allyl metal complex formation was taking place, we should get both the same product in both the reaction, but here we are getting a different product in measure yield, right? Measure selectivity. So because of this one, we can say that the reaction is not going through the pi allyl metal complex formation, but the reaction is undergoing via sigma plus pi complex formation. Why? Because if this is the case, this is the first case when pi allyl formation will takes place here, metal bind over here, then we will get this as a product. When the other case will form, in this case, because we have just switched the isopropyl group, so we will get this as a major product. So this is the uh, proof that we are getting a different intermediate, but the same product ratio is proving the reaction mechanism. So this is a similar type of intermediate, we can say, form in both the reactions. Now, talking about the crossover experiment. So this is mainly useful in a rearrangement reactions. So here we can see, we suppose we have A, B and A star, B star as our reactant. Sorry. Right? Suppose we have our reactant. So when it will get converted to product, we are written here C, D and C star, D star for showing the corresponding product. So if we are getting the same product without crossover, means this B is not interacting with the A star and this A is not interacting with B star, and that's why they are giving a no crossover product, right? But if we have a crossover product, what will happen? First, they will give a simple product like AB will give CD and A star B star will give C star D star. But when the crossover will happen, what can be the possibility? This A star can form a bond with this B star, which will give you the product C and D star. C is representing A, right? D star is representing the B star after product formation, right? This is the one possibility, and the other possibility is that this B can react with A star, so it will give you C star and D. This B is giving a D and this A is C star, correct? So this is called a crossover product. We will give the example, then it will be better to understand you. Now the first example is a Claisen rearrangement. So here we will see that crossover is taking place or not. So suppose we have a reaction, this as a substrate. So as we have learned till here, we know this type of reaction undergoing via rearrangement reaction, that is 3,3 sigma tropic shift. So all of you know that 3,3 sigma tropic shift is a concerted process. So when the reaction undergoing concerted intermediate, what will happen? The bond breaking and bond making is happen simultaneously, right? So that's why the this bond breaking will takes place with the same speed when the bond formation will takes place. So there is no possibility for crossover because immediate bond formation is taking place. There is no free fragment uh, or any charged species to interact with the intermediate, right? So immediate formation of product will takes place here. Similarly, here also you can see 3,3 sigma tropic shift, which will give you a product C star D star here, right? Now talking about the other way of mechanism, like if it will undergo undergo via radical mechanism or a cationic or anionic mechanism, then what we will observe? Here we will observe radical formation. We have discussed this earlier also. So radical will form here, and in this case also radical will form here. So here one is the possibility of formation of product is that they will this radical will trap this sorry, one of the possibility for formation of product is this radical will undergo here, right? We have discussed already. Then this will give here radical. This is hook arrow radical, right? And this radical will trap the this radical to give the product. This is a straightforward product formation, or it can undergo this way also. Here radical will generated and it will attack here also, right? So this is a possibility when it will give a CD product. The in both the cases this is the first possibility. The other possibility is that this radical can interact with this radical can interact with this radical to give a crossover product, right? To give a crossover product. And in other same case here also this will undergo this way radical, then here, and here the radical will generated will attack on this radical to give the other crossover product. So here we will observe four different types of product, right? In similar way in cationic anionic intermediate also the process will be same. This negative charge will form bond over here, and here the negative charge will be generated over here, right? And this negative charge will attack over here to give a common product, which what we have observed in concerted process. The other possibility is that this negative charge can attack on this carbo this double bond. This bond will get isomerized to give the crossover product. So this is the possibility for getting the crossover product. So in crossover product we will get four different types of product. But what we observed from the reaction experimental section, we observed that only two product formation is taking place. That means the reaction is going via concerted mechanism only. So this is a correct way and a very efficient way to find out the mechanism of the reaction. Here we can say the mechanism is going via concerted mechanism only because we are observing only two product formation. If there was a different type of product formation was there, then we can say the reaction is going a fragmentation intermediate or other intermediate, radical intermediate. But here this is not the case. So I hope all of you are clear here. Then the other example we also have benzene rearrangement, right? So like we are talking about the rearrangement reaction. So all of you know all the rearrangement reaction mostly when it's going via concerted mechanism, the bond breaking and bond making is taking place simultaneously. So that means there is intramolecular reaction is taking place. No external species are participating in reaction during the concerted mechanism. So suppose here we have our benzene and R is a group present on each ring. So R might can be possible OMe group and it can be a OET group. So it's a mixture of both the group. So if you will get the crossover product, what will be the possibility of the product? If this mechanism is going via different mechanism, this reaction is going via different mechanism, then you will observe, you will think that this NH bond is breaking, and then the new bond formation is taking place at the para position of each benzene ring, each phenyl ring, right? Now, if this is the case, breaking and then bond making, then each will contain OMe group, right? Then when it will undergo crossover reaction, it will give four different types of products. The one possibility is that OMe, both the R group will be OMe, and the second possibility is both the R group will be OET and OET. And in the other case, crossover product, you will observe one R group will be OMe and the other one will be OET. But when people have performed this reaction, they have observed that only two types of product formation was taking place, where both the R group was same in both the cases. That means there was no formation of crossover products was taking place. So because there is no formation of crossover product, that means you can say the reaction is going via concerted mechanism. So what will be the possibility of the mechanism? Here you can see it will undergo 5-5 sigma tropic shift. So we have discussed the sigma tropic shift reaction. So here when the 5-5 sigma tropic shift reaction will takes place, what will happen? 5-5 new bond formation will takes place here. You can see with the red ink here. Then bond breaking will takes place over here to give the corresponding product. So because this is a concerted mechanism, that's why we are not observing any crossover product. So I hope all of you are clear in this case also. Now let's discuss the catalysis. So till here we have discussed the trapping and intermediate formation, different intermediate formation and crossover experiments, right? Now we are going to discuss the catalysis. What is catalyst? Anyone have any idea about this term? It's an English word term. So as you can see on screen, the catalyst is a species or a compound, we can say, which takes part in a reaction and affect the rate of reaction by increasing the rate of reaction, but it is not consumed during the overall reaction. So at the end of the reaction, catalyst will look like unaffected, right? It will get back in its original form. So, catalyst is mainly used for lowering the activation energy of the reaction. So, that's why catalyst is very important. So, there are two types of catalyst. One is homogeneous catalyst and other is heterogeneous catalyst. So, what is homogeneous catalyst? So, the catalyst which have same phase with the reactant and uh, other solvent possible in present in the reaction. So homogeneous means it has homo phase, means same phase. Because of same phase, it's called as a homogeneous catalyst, which is soluble in the reaction medium, right? The second thing is heterogeneous catalyst. So heterogeneous catalyst is insoluble in the reaction medium, means the phase of the catalyst will be different from the phase of the reactants and solvent and products. So the example for heterogeneous catalyst is that when you are performing a gas reaction and you are loading a solid catalyst. So on a solid surface, some molecules are uh, uh, adsorbed. I hope all of you know adsorption. So on solid surface, some molecules are adsorbed and they are reacting with the gaseous phase of reactant. So they are catalyzing the reaction in heterogeneous form. So you can take a different example of heterogeneous catalyst. In industries there are flow reactors used. So in those reactor the gas phase reaction is taking place, and the catalyst is loaded in a solid form, and it's catalyzed the reaction. So that's why, because of different phase, it is known as a heterogeneous catalyst, and homogeneous catalysts are soluble in the reaction medium, and then it catalyzes the reaction. So mainly homogeneous catalysts are used in a liquid phase reactions, and heterogeneous catalysts are more common in gas phase reactions. Now this is a reaction coordination diagram for catalysis, right? So when you are performing the reaction from A to B, your reactant A is getting converted to B. It will give you some transition state energy, right? Activation energy. But while it will undergo reaction in the presence of any catalyst, then what will happen? The activation energy of the transition state will lower, and it will provide the a low energy pathway of the reaction. So here all of you know that y-axis we have potential energy, and on x-axis we have a reaction coordinate, right? So when our reactant is A is participating in reaction without catalyst, this is the case without catalyst, no catalyst. No catalyst, right? So when we don't have any catalyst, then it will give you a large activation energy. Large activation energy. Sorry, this is right. When it will catalyze by the some catalyst, then what will happen? The activation energy will get reduced, right? So the hump we can say this hump will get reduced, and we will get low activation energy for formation of our product. So this is a simple way to explain the catalyst effect, but no, this is not the actual case where when the transition state will look like. So what will be the realistic picture? Here we have given, when the catalyst was added, actually it changes the path of the reaction. It's not following the same path. So because it's formation of different types of intermediate is taking place, so it changes the path of the reaction to give the we cannot say the path, but the different intermediate formation is taking place to give the particular product. So you can say when the catalyst was added, it forms a complex with our reactant, which when the complex formation is taking place, that complex is stable compared to the reactant, right? So stability you can see here, a catalyst complex formation is more stable than the A. Then after A catalyst complex, it will again undergo B catalyst complex, which will give some activation energy which is higher than the first step, right? So after getting B catalyst complex, it will convert it to product B, and it will give a particular product in low activation energy. So you can see here, compared to the this much high activation energy, this is the low activation energy. So that's how the catalyst is favoring the reaction to form the product in uh, fast way. Fast way. We can say catalysts are increasing the rate of reaction by lowering the activation energy. The other case is also there where when the path will be completely different. So this is that is called a complete different path followed by the reaction to give the corresponding product in that case, if the path is different, the intermediate will form during the reaction will also be the completely different one. Okay. Then what we have learned here? Yes. Yeah, you have already assignment question, right? Huh. So that type of question only comes in exam only from these topics. So as I'm discussing in few questions in my lectures, so that type of questions are only will come in exam. So I cannot discuss more questions because I have I am not I have told by ma'am that I have to discuss only a few questions which is not given in assignment. So I cannot solve all the questions. So just the concept is important. Okay. So here we have discussed the crossover experiments. Then we have discussed the catalysis and definition of catalysis. All of you know that catalysts are taking part in the reaction but not consumed in overall reaction. And catalysts are used for essentially lowers the activation energy. So reaction coordination diagram we have discussed. We are going to discuss in a deep look. Now all of you know that these topic have already taught by ma'am, but I'm just revising this topic. So if you have any doubt during these reactions or this session, you can ask me. Now here we have a reaction coordinate diagram. Suppose we have here this is a conversion of A to B with a act, some activation energy. When we are using catalyst, then catalyst will form a complex with A and which will have a more stability compared to the A. Then it will again undergo the transition state to give the B catalyst complex. So this is the transition state activation energy which is given by red arrow, right? So when this is the case, so you can see the A stability is stability of A is less than A catalyst, right? A catalyst complex. So from here to here, activation energy will be low compared to this one stable one, right? So which will be a favorable one. So all of you know that low and activation energy is always favorable. So this is already favorable. So this catalyst is not working in a proper manner. So this is the not the suitable catalyst. So we can say it's not increasing the rate of reaction, but it in some case we know that it increasing the rate of reaction. So this is not the good catalyst. Now in second case you can see the A is getting converted to B via A catalyst complex and B catalyst complex. Now in presence of catalyst, you can say the activation energies remain unaffected. Very slight changes there. So very slight changes there. That means this is also not the suitable catalyst for this particular reaction, because if it's the suitable catalyst, it should reduce the activation energy by a significant amount, but here we cannot observe the activation energy change. So that's why this is not the suitable catalyst. Now in third case, here you can see again that because here you can see that tight binding of catalyst to A is there. That means A catalyst bond is very strong and this is a stable intermediate. But the weak interaction in transition state. So in transition state it has weak interaction. That means the weak interaction means less stability. Less stability means higher the energy, right? So that's why the energy will become higher. So transition state value will become high. So again you can observe the activation energy difference. So there is no change in activation energy. That means this is also not a good catalyst. Now talking about the fourth case, here you can see tight banding of A is there. A catalyst bond is very strong, and along with this very strong banding with transition state is also there. That means this transition state is more stable, right? Strong banding means more stability. All of you know that strong bonding means strong stability. So because of more stability, the activation energy will become lower, right? Because the activation energy, now you can see the activation energy difference. So here the activation energy is much lower than the first case, right? This green one, this energy and activation energy is much lower than the this green A activation energy, which is a without catalyst form. So we can say in that case this is a good catalyst for the reaction, which increasing the rate of reaction, correct? So I hope all of you are clear here. Then now we are going to discuss the types of catalysis. So there are different types of catalysis: acid base catalysis, banding catalysis. In banding case, all of you know that uh, catalyst is banded with a intermediate. Then in acid base catalysis, you know that acid catalyzed reaction, base catalyzed reaction. We are going to discuss this one, which is very common example. Then electrophilic catalysis, nucleophilic catalysis, strain and distortion, covalent catalysis, and phase transfer catalysis. Now first case is our acid base catalysis. Now we are going to discuss the acid base equilibria. So all of you know that when acid base reaction is taking place, the formation of conjugate base and conjugate acid is taking place. I hope all of you learn this reaction in your lower class, previous class, right? So here the acid will give a conjugate base, and base will give a conjugate acid. So when acid base reaction is taking place, always you can observe that acid is losing a proton, right? Proton elimination abstraction is taking place from acid, which will give you a conjugate base, and base is accepting the proton. So if you learn the concept of Bronsted acidity and basicity, you will observe that in all the Bronsted acids are donating the proton, and Bronsted base are accepting the proton. Here the concept of Bronsted acidity and basicity is taking place here. You can see this is conjugate base, right? So if you see the reaction in this direction, this base is taking a proton, it's accepting a proton, that's why it is a base, right? And this is conjugate acid. When you will observe in this direction, same direction, you will see that this because it is a conjugate acid, it's donating the proton, right? As I told you, proton are in Bronsted all the Bronsted acid are proton donating, and Bronsted bases are proton accepting group. So that's why this is a conjugate acid. Now if we are looking in a forward direction this way, then this is acid because it's donating the proton, right? Proton abstraction is taking place, that's why here it's acting as an acid, it's a proton donor, right? And this is base because it's a proton acceptor, we can say. So that's why here you can see it will become BH. So here it is acting as a base. So I hope all the examples are clear to you, right? Now let's talk about the acid dissociation constant, which is called as Ka. So when the dissociation of acid will takes place, what will be the rate equation? So all of you can see here we have learned how to write the rate equation in previous classes, right? So if talking about this reaction, K equivalent will become equal to product upon reactant, right? We always know done the equation like this way only, product upon reactant concentration. So here reactant is product is our A minus N H3 plus O, right? So here we have a concentration of product, then concentration of reactant. This is the K equivalent equation. Now if we will fill the value of Ka of water, because here we know water have used, so the Ka value of water is 55.5. So we will substitute the value of Ka of water, then we will get this equation. Then this 55.5 can go to the other side in multiplication, right? Here it was in denominator, it will go to numerator, that is multiplication. So here we will observe this intermediate, right? Now after getting this intermediate, you can say acid dissociation constant equation is become this way, right? So here Ka value will become 55.5 into K equivalent. So here you can see Ka value is ranges from 10 raised to 12 to 10 raised to minus 50, which is a very greater great range. So we cannot predict here Ka value properly because the range is very high. So because of this one, uh, we have calculated the Ka value in terms of pKa. So pKa is nothing but pK is equal to minus log 10 of Ka. So this value is indicating the effect acidity of the substrate or any acid. So here you can see if the low pKa value is there, that means it indicates that the acid is very strong. So lower the pKa value, more the acidity of the reactant, right? More the acidity. So you can remember this point. Whenever you are observing the low pKa value, that means that that particular acid is a very strong acid. Okay. Now this is a simple reaction we can use for a pK value comparison. Now we have here, sorry, acetone, right? This is our acetone which is undergoing reaction with base to give the particular enolate ion. Now here you can see our if we are talking about the acidity of this acetone, we are here labeling as acid 1. Acetone is labeled as acid 1, which have a pK value, some pK value, right? And while it undergoing a reaction, it's giving its conjugate acid and conjugate base, right? We have discussed it here. Conjugate base and conjugate acid formation is taking place. So this acid will give a conjugate base and this base will give a conjugate acid, right? So after getting this conjugate acid, now you can see, suppose we have here OH as a base and it accepting the proton to give the water. Now all of you know that water or suppose methanol, its acidity is more than the this acetone acidity, right? So pK value for this acid, sorry, this conjugate acid pK value is lower compared to the this acetone pK value, right? Sorry for the confusion, sorry. Here is water which is neutral and this acetone is slightly acidic. So pK value of acetone is more than the pK value of water and methanol. So because the pK1 value is low, that means it is a stronger acid, right? It is a stronger acid. So whenever the acid is stronger, uh, it has lower pK value, that means the reaction will go in a forward direction. right? So here some rules are there for predicting the relative acidity is important. So two principles are there for neutral acids. Compare stability of conjugate base. More stable conjugate base implies more acid, a more stronger acid, right? And for cationic acids, compare relative stability of acid themselves. More stable acid will be the weaker acid. So this is for two different cases. For neutral acid case is different and for cationic acids is different. Now we will discuss some example. Hmm. So here you can see the we have what we have discussed in catalysis. So this is for you only. You just observe this slide and revise yourself what we have discussed in earlier class. Then now we are talking about here acid base catalysis. So here pK value. So acetone pK value is 20 is given here, right? Now water pK value is 15.7. So all of you know that water pK value is low. So here I think is mistake is done here. Sorry, not a mistake. Yeah. So pKa2 is showing the value for water and pKa1 is value of acetone, right? So because pKa2 is low, that means water acidity is more. Water acidity is more, that means it is more stable, right? Stability will be also there. That means when we are doing the reaction, water form formation of water is taking place, which is stable because it is more acidic. Because of this conjugate acid stability, the reaction will always go in a forward direction. So ma'am have given this sign, so all of you do the correction over here. So this is the more actual case. pKa1 will be more than the pKa2. Here the value is 20 and here the value is around 15. Sorry for the disturbance. Yeah. So because of this stability, this reaction will go in forward direction, right? Now we will compare the pK value. Relative comparison of pK value is here. So acetone have 20 pK value, water have 15.7. So water have more acidity. Now let's talk about the ethyl acetoacetate. Here we have ethyl acetoacetate. Sorry. Here now you can see the acidity of ethyl acetoacetate is more compared to the acetone because of the stability of resonance structure, right? Here if you will see the structure, this can undergo resonance type of structure, right? This way. So here the stability is more compared to the acetone. This is the case of diethyl malonate. Here the case of diethyl malonate. Now here also you can see this is a ester and there is more resonance or delocalization of electrons are there. That means it is a more strong acid. So because of the more strong acid, it will give a pK value of 12.7, right? Now talking about the methanol. Methanol is slightly more acidic compared to the water, and compared to acetone it is more acidic. Same case in ethanol also, and ethanol is slightly more basic. Why? Because one CH3 group is added, which is our electron releasing group. So it is a destabilizing factor in acid form. So that's why, because of electron rich presence of electron rich group, it's giving a more higher value. Now diisopropylamine is giving a very high value, that is 36, means it's showing a basic property. So all of you know that amines are basic, so that's why it's giving a less pKa value. Now in this case also nitrogen ammonia is present, so it's giving a basic value only, that is a more high pK value. Talking about the methane and hydrogen, so methane is giving a very high pK value, that is very least acidic form. And talking about hydrogen, hydrogen is also very less acidic, because it's a hydrogen is H radical, always remember. So this is electron rich species. Electron rich species are less acidic, showing a greater pKa value. Now factor affecting the acid strength we are going to discuss here. So here we have a common acid base reaction. Then reaction medium or a solvent is also affecting the acidity of the reaction. Now solvents are very important in the reaction. So better solvation of ion will improve the acidity. Now talking about the acid, suppose this is our acetic acid. Acetic acid will give a low pK value in water, but while talking about the methanol, DMSO and DMF, the pK value will get increased and it will give a high pK value, that means acidity will get reduced. So this is the case because of the solvation. The solvation is not good in DMF, DMSO and methanol. That's why the acid pK value is getting lower. So in case of water, the solvation is very good. That's why the acidity is very high compared to the other solvent. Now paranitro benzoic acid is given here. Now paranitrophenol is here, not benzoic acid. Here you can see in water it's giving a pK value of 7.16. Now in case of methanol, DMSO and DMF, again because of the solvation, the acidity is getting decreased. Then that means the pK value is getting increases. So in case of here phenyl amine, NH3 plus is there. So all of you know that it is a base, nitrogen is present, it's a base, but pK value is in water is showing 4.6. But when talking about the DMS and DMF, the pK value is getting reduced because of high solvation. The solvation of this phenyl NH3 group is more in DMSO and DMF compared to the water. That's why the pK value is getting reduced, and that means the acidity is increases in DMSO and DMF solvent. So solvents are very important when we are talking about the acidity. So they are playing a very important role. Now the second factor is that electronegativity and induction. So electronegativity of the atom next to acidic hydrogen influence acidity. So now we will discuss here acidity. Suppose we have here hydrogen and next atom is fluoride, fluorine, right? Hydrogen fluoride we can say, and this is a very electronegative atom, very much electronegative atom. Now talking about this H is next to the electron releasing group, Cr3. R is a alkane, so it's a electron releasing group, right? Now talking about this case, this is a alcohol where oxygen is electron withdrawing group, right? More electronegative group, and here also the more electronegative group. Now as we have discussed that more the electronegativity of the atom next to the acidic hydrogen, more will be the acidity. So here which is the most electronegative atom? Fluorine, right? Fluorine is the most electronegative atom in a periodic table. So HF is the more strongest acid. The pK value will be more lower for this case. So that's why HF is a very stronger acid. Now after fluoride, which one is a more electronegative? Oxygen, correct? Oxygen is a more electronegative compared to the nitrogen and carbon. So that's why alcohol will be our second in terms of acidity. Now talking about the third case, all of you know that nitrogen will take the position of third because of the higher electronegativity compared to the carbon one, right? And because Cr3 is a electron releasing group, that's why it will give a lowest acidity to the this proton. So that's why this is the least acidic. So I hope all of you know this trend. Now talking about the third case, which is resonance stabilization. So what is resonance stabilization? Now this is a third factor. So here suppose we have our molecule methanol here, methanol, right? Now talking about the phenol, here we have aromatic ring, right? In methanol, all of you know that there is no uh, conjugation or double pi bond form. Pi bond is present in methanol, right? That's why it's showing the pK value of around 16, not the exact one but around 16. While we will replace this CH3 group by aromatic ring, we will observe that now this aromatic ring will stabilize the negative charge here, because this negative charge is getting stabilized by the pi bond of the aromatic ring. The pK value will get reduced. So that's why stability will be there. That means pK value will get reduced, and that's why it will give you a more acidity. Now talking about the substituent on this aromatic ring. If we have the electron withdrawing group substituent on this aromatic group, aromatic ring, then what will happen? The this resonance will get extended, right? We have discussed the resonance structure this way: oxygen, then oxygen, and this resonance will go this way, right? We have discussed already. So because the resonance stabilization will increase here, that's why the pK value will also get decreased. So because the pK value is get decreased, that means it is more acidic compared to this one. Now adding the another nitro group on the ring, we will observe again the increase in acidity by decreasing the pK value. Now when we will add the 3 nitro group, we will observe the great, sorry, what is it? We will observe the greater acidity compared to the other species we have taken here. So this is the more acidic and very low pK value molecule, right? It is a more acidic. Now talking about the second example. Sorry for this one. Yeah. Now talking about the second case. Here we have CH3 group toluene, right? This is the example of toluene. Here you can see if proton will be abstracted from here, we will get negative charge here, right? Then this negative charge will get stabilized by this aromatic ring in resonance stabilization. But here this is a electron rich species, right? This is not that much electronegative compared to the here O minus. That's why the pK value is higher in this case. Now when we are adding the another aromatic ring on this carbon atom, we are observing the pK value decreases, right? Why? That means here acidity is increases. Why is the case? Because here resonance stabilization is increases by these 3 pi bond, right? Now the this minus charge is more stabilized because of the another aromatic ring. That's why the pK value is getting reduced and it's giving a more acidity. Now talking about the third case, when we will add one more aromatic ring, we will observe the against pK value lowering the pK value, but the difference is not that much high. Why is the case? Because here the steric hindrance will takes place. So because of the loss of planarity, that means the molecule should be planar for resonance. All of you know that, right? But when the three phenyl group will come across each other, it will not become more stable because of steric hindrance. So this will slightly get changed like a fan wings. All of you know that fan wings are slightly tilted. So in this way, this will become slightly tilted. So because of the loss of planarity, it will give the low stability. Because of low stability, pK value will not become that much low. So acidity will get reduced. That's why the value is not that much differentiable, right? Only slight difference is there. The second factor is that saturation of stabilization. So here already the molecule is very much stabilized. When you are adding one more aromatic ring, it's not getting that much stabilized because it was already stabilized. So that's why the saturation of stabilization is taking place, which is not giving a more stability for the molecule. That's why the pK value is high here. Now let's talk about the fourth factor. The fourth factor is bond strength. So within a group, is acidities usually increase with decreasing bond strength acidity of HI. So here I will going to discuss the bond strength. So the stronger the bond, more the pK value. So while comparing the acidities of molecule not within a group, this is not a major contribution factor. So this bond strength is a very unusual case of acidity, means it is not always useful. So when we are talking about the major bigger molecules or other major molecule, when these bonds bonds are present, that time these comparing acidities are not a major contributing factor. So this is not mostly used here, but because it's a part of factor, that's why we are going to discuss here. So in case of acidity, HI will have more acidity because HI bond is very uh, weak compared to the HF one. So HF bond is very strong. HF bond is very strong. Why it is very strong? Because the size is also matters here. All of you know that iodine size is, if you will write the hybridization, sorry, electronic configuration, if you will write here, you will observe that the iodine size is very high compared to the hydrogen one. So that's why the bond is also very weak. But in case of HF, there is a bonding also, and HF bond is very strong because of same size. So that's why in halogen you can see when the bond length is high, more, and bond strength is low, that means the acidity is high, right? So the sentence is given here. Usually, acidity usually increases with decreasing bond strength. So bond strength is decreases in HI case. That's why acidity is increases. Because this is not the important factor, that's why I'm not going to discuss in detail. But this much is enough, I think. Now let's talk about the fifth factor, that is electrostatic effect. So what is electrostatic effect? So positive charge next to the conjugate base will stabilize it and the negative charge will destabilize it. That is called the electrostatic effect. So suppose we have here acid. Yeah, right. Here the pK value is 4.82. So its what will be its conjugate base? Anyone know? This is conjugated base, right? Conjugate base. So if this is a conjugate base and the charge next to conjugate base, if it's positive then it stabilize it, and if it's negative then it's destabilize it. So here you can see this is a negative charge. That means this is it's destabilizing this one, destabilizing this one. That means the reaction will not go forward direction. This is a more stable acid. This is a more stable acid. So that's why the pK value of this one will be lower compared to this one pK value, right? If you are not understanding, then you can ask me in between. Right? Now talking about this case, second one. Here also negative charge will generate over here in conjugate base, which is destabilizing it. That means conjugate base is less stable compared to the this acid. So that's why the pK value of acid will be lower compared to the conjugate base pK value. Now talking about this case, here you can draw its conjugate acid. Yes, this conjugate base will be this one, right? Conjugate base. Now here you can see negative charge is there, right? And this negative charge is stabilized by this phosphorus PPS3 group. So this is more stable compared to this one. So that's why this halide is more important and the reaction will take place in forward direction, right? So it stabilizes. This positive charge stabilizes the conjugate base. That's why it is more stable. And pK value of this one will be lower compared to this one. Now the sixth factor is hybridization. So I hope all of you know about the hybridization sp, sp2 and sp3. So in sp3 we don't have any double bond. In sp2 hybridization double bond is there, and sp hybridization we have triple bond. So while talking about the acidity, when the S character is increases, the acidity is also increases. This is a direct relation. So S character is here, if we are talking about sp hybridization, here 50-50% S and p orbital are there, right? 50-50%. S character is 50%. While talking about this one, here P is double and S is 1. If talking about the this hybridization, 33% of S is there, right? 33%. Now talking about this sp3, here 25% of S character is present. 25%. Right? So as I told you, when the S factor S percentage is increases, that means the acidity is also increases. So in case of SP, the more S percentage is very high, that means it is more acidic. So in this basis, we can calculate here acid pK value. We can give the relative pK value. So here we know that C triple bond N is present. That means there is more S character. That means the pK value will be more lower. Lower the pK value means higher the acidity. So this is as much as lower than minus 12. That minus 12. Now talking about here, this is a sp2 hybridized. That's why the pK value is lower compared to the sp3 hybridized one. This one, right? So I hope all of you know the relation of pK value here. So this is the sixth factor. Now talking about the seventh factor, that is aromaticity. Suppose if you have any acid and it will the conjugate base of that acid is more stable, more aromatic compared to the acid, that means that that acid have higher pK value. Like talking about this one, this is a acid. Suppose after proton abstraction, proton donation, negative charge will generate here, right here. This is the case. Now this is the aromatic ring, right? Aromatic compound. You can follow the rule 4n plus 2 pi electron. So this is following the rule. So that means this is the aromatic compound. So because of the aromaticity, it will become stable. So the pK value for this intermediate will be lower compared to this one. So that's why this is the stable conjugate base. Now talking about the other case, here you can see the pK, because of stability, this is the more acidic compared to this one. Now talking about here, you can see the intermediate after proton elimination, it will become anti-aromatic. Anti-aromatic is least stable compared to the aromatic. That's why the pK value will be higher in this case, and it will give a less stability, less acidity. So I hope this seventh factor is also clear to you. If you want to know more about the aromaticity, you can see the paper here, Bordwell acidity paper, when the pK value of organic acids have compared. So you can go and watch, read that paper also if you want more detail. So we have discussed these factors, right? Acid base catalysis we have discussed. Then for neutral acids and cationic acids also we have discussed the acidity. Now we have discussed the different factors, that is solvent, electronegativity, resonance, bond strength, electrostatic effect, hybridization and aromaticity. Now let's talk about the Bronsted acid base catalysis. So all of you know that proton or hydroxide are involved in Bronsted acid base catalysis. So these Bronsted acid catalysis lowering the transition state energy, right, and regenerated at the end of the reaction, that is called catalysis. This is a definition. But when talking about the reaction here, it's accepting the proton to give the particular product, right? Here you can see that proton is getting consumed by the reactant. Consumption of proton is there. So that's why this is not called as a Bronsted acid base catalysis. It will called as a acid base promoted reaction. Promoted, not catalyzed. Because if catalyzed reaction will be there, then at the end of the reaction the catalysis should be remain unaffected. It should look like unaffected, right? But here this is not the case. So that's why this is called, this reaction will be called as a acid base promoted reaction, not the acid base catalyzed reaction. Okay. Now let's talk about the classification of catalysis Bronsted acid base catalysis, where we have specific catalysis and general catalysis. Talking about the specific catalysis, in specific catalysis, proton transfer occur before rate determining step. So the proton transfer is very fast in this case. So it occurs before the rate determining step. So now specific acids are there, where we have protonated form of reaction solvent like water. This is H3O, right? So protonated water is there. So this is a specific acid. Now here also proton is there. DMSO have one proton, that's why it's become specific acid. These all are specific acid example. Now talking about the specific base. So conjugate base of reaction solvent are there, like conjugate base, as I told you the difference between conjugate acid and conjugate base. So here the proton donor, so OH minus will act as a specific base. Here DMSO with one less proton will behave as a specific base, and here acetonitrile base. So I hope all of you are clear with specific acid and specific base examples. Now we will learn about the kinetics of specific acid catalysis. So reaction in water is taking place. So this is specific acid, right? So the proton transfer is fast from the rate determining step. We have already discussed here. Sorry. Yeah, here, right? Before rate determining step. So that's why proton transfer will take place, and then rate determining step will done. So we will get pH as a product. Then proton transfer again will be fast in this reaction, and we will observe product and along with specific acid. So acid will so you can see here this H3O will remain as it is at the end of the reaction. So that's why it will called as a catalyzed reaction. So specific acid catalyzed reaction. Now let's talk about the rate of the reaction. So while the writing of the rate of the while writing the rate of the reaction, all of you know that we are writing the rate determining step reaction, right? So here rate determining step is this one, and we are considering K as a rate constant. So K will be here, and reactant concentration will be our rate determining step, will become our rate equation. This is our rate equation. We have discussed how to write rate equation in previous lecture. If you are not understanding, you go and watch that lecture. Now, yeah. Now talking about the reaction equation, you can see here this is the equilibrium reaction, right? In back direction also. This is the reaction, equilibrium reaction. Here water is there. So here we are talking about the KARH plus reaction constant. So this is the reaction constant here, and we are writing a rate constant equation. So first we are writing K equilibrium reaction for this reaction, right? So this is the reaction we have. After, so if we will write the rate constant equation here, K will become equal to reactant upon, sorry, product upon reactant. So here you can see here this one and divide by this one. This is our K equation. Now talking about the Ka value. Ka value is nothing but this equation by eliminating water. Water is neutral here. So we are talking about here only charged species. So that's why we have written as a Ka value as a this one, right? Now putting the writing the RH value here, it will go this side and K will come on denominator side. So the equation will become this way, right? and while we are substituting this equation in our rate equation, we will observe the rate equal to KRH3O plus divided by KARH plus, which is rate constant. So uh, we can say that this is a K observed, and H3O plus is our specific acid, right? So the rate is depend on our specific acid also, and so in short, the rate equation will become K observed into concentration of R, because in denominator K is there, right? And H3O plus is a catalyst, specific catalyst or water, we can say. So that's why the rate will become this way. So this is a kinetics of specific acid catalysis. Now talking about the reaction in water with acetic acid added. So here you can see we have here acid reactant our, and this is a specific acid water, we can say. Now you can see it will get protonated and A minus will generated. Now the rate determining step will takes place to give the protonated product plus A minus, then the proton transfer will be very fast and it will give a product, right? So this is the reaction which we have discussed earlier also. So now the rate will become, for rate determining step we are finding the rate will become KRH, because the K is a reaction constant, dissociation constant, and here RH is a reactant. That's why we are writing KRH. Why we are not writing A minus? Because we have done that this is our catalyst, right? We are writing only in terms of reactant. So now K equivalent will become what? This is our K equivalent. So we have discussed earlier also, the equation will become RH plus A minus divided by RHA, product upon reactant, right? This is the rate equation, K equilibration. Now talking about the here the RH value, if we will rearrange this value to get the RH value, and we will substitute this value in the rate equation to get the rate equation here, right? Now we know K, we have to find out the Ka value also, which is this reaction. So here also we will write the product upon reactant upon product. So this is the first step. Again we will write the Ka equation will become Ka minus H3O plus divided by Ha, which will give you the value of Ha. Here you can see, if we are adding the acetic acid, so Ha will go here this direction, this A will go to the denominator to give this equation, now it will become H3O. So we have rearranged this equation to get this value. Now substituting this value in rate equation, we know that K is our rate constant, then K equivalent is equal to, we are substituting RH value here. So RH value is K equivalent RHA divided by A minus, right? So here we are writing our that value. Then we know that this HA value we are substituting here instead of this one, right? So H3 plus O and KAHA, we are substituting this value instead of HA by A minus. So we are getting this as a rate equation. So from here also we can see that H3 plus O, this is specific acid, is a specific acid catalysis which is used in the reaction, and the rate of reaction is depends on this specific acid catalysis also. So the rate equation is become K observe into concentration of R. So I hope this kinetics is understood by you. If you don't understand these things, you can ask a question or you can go and watch ma'am's lecture which is available on YouTube. Now let's talk about the specific base catalysis. So here in specific base catalysis, what we have, as we have discussed here, in a specific base, the conjugate base of reaction solvent will be there, right? We have discussed that. Deprotonated form, we can say. So here we have here base, and it will become, the proton transfer will be very fast compared to the rate determining step we have discussed earlier. Now it will become R minus and BH plus, right? In previous case, it was giving a proton in specific acid catalysis. Now it is a specific base catalysis. That's why it will give you a proton abstraction. Now after rate determining step, you will get P minus and BH plus, which again the proton transfer will take place faster and it will give you a product pH and base. So base will remain unchanged at the end of the reaction. That's why it is called as a specific base catalyzed reaction. Now talking about the rate, always we are writing rate in terms of rate determining step. So here the rate determining step will become our rate of equation. So rate equal to K R minus, right? R minus. Now we will substitute the value of R minus by calculating it from equation. Here we are taking this reaction RH plus water. Instead of B, we are writing here water base. Now it will become R minus and H3O plus. This is a proton transfer reaction forward direction, right? Now we are writing the rate equation by writing Ka value. All of you know that we are writing product upon reactant. So we are writing here KARH value R minus. Here it is given R minus H3O plus and divide by RH, right? After getting KARH value, we will rearrange this value to get the value of R minus, right? Here R minus will remain this side only. RH will become numerator here and this will go down to denominator like this, right? After getting this R minus value, we will substitute this value in our rate equation and we will observe the rate equal to KARH RH concentration divided by H3O plus concentration. So rate is depends on this H3O also. So in the specific base catalysis, what you have observed, the H3O plus concentration is in denominator. That means the increase in concentration of H3O will decrease the rate of reaction. While in case of the specific acid catalysis, it was in numerator. Numerator means it was directly proportional to the rate of the reaction. Now let's talk about the specific catalysis plots. So what will a plot of K observed versus HA look for a specific acid catalysis? So as I told you, in acid catalysis it was directly proportional, right? So when the pH value will be higher, pH value means acidity will be higher, that means the K observed value will also be higher, right? I told you here this is inversely proportional, this is directly proportional to the rate, right? So when the pH value of this H3O plus will become higher, that means acidity will become higher, not pH value. pH value will lower, pH value indicating the high acidity, right? So acidity will be higher, then the rate will also be higher. So here you can say acidity pH2 is a higher acidic, right? So acidity is more, that's why K observed value is more. Now in this case acidity pH7 is showing a lower acidity, that means K observed value is also low, right? Now talking about the base catalyzed specific base catalysis reaction, you can see more the pH value, that means less the acidity. Less the acidity means more the K observed value. I told you here the relation is inversely proportional. If the acidity of as specific as base catalyze will increases, that means the rate will decreases. So here acidity is increases in this case, right? So that's why K observed value is decreases, and here acidity is increases. Sorry, acidity is decreases. That's why K observed value is increases. So I hope you understood this relation. So this is a graph for specific acid and specific base. So here we were talking about the K observed value only, right? K observed value, K value. Now we are going to talk about the log K observed value. So versus pH. So when the pH increases in specific acid, the log of K observed is getting decreases. pH increases, log of K observed value decreases, right? pH increases means acidity decreases. Remember the relation. So it will give you a minus slope, that is minus 1. Now talking about the specific base, when the pH is increases, the log K observed value is also increases. So that will give you a positive slope 1. So this is the relation between the specific acid with pH and specific base with pH. So I hope all of you are clear to here. If any question, any doubt is there, you can ask me in between. Otherwise, that's the content for today's lecture. We are going to discuss the new topic in next lecture. Any question? Thank you so much for your kind attention. So I am stopping here. Welcome. See you in next lecture.